Today, we are going to be learning how to solve the equation to calculate mechanical advantage for a Class 1 lever. If you remember, there are three different classes of lever. Today, we're learning how to use the Class 1 lever. As you can see from the diagram, the load is at one end, the effort is at the other, and the fulcrum is somewhere in between. The equation for the mechanical advantage of a lever is calculated by dividing the distance from the fulcrum to the effort by dividing the distance from the fulcrum to the load. You can see that in the equation below. The problem that we're going to solve states that there is a 360-pound object resting on one end of a board that is 5 feet long. If the fulcrum is located 1 foot away from the weight, how much effort must be applied to balance the system? To begin with, we should sketch a Class 1 lever. If you remember, the load is at one end, the effort is at the other, and the fulcrum is somewhere in between. In our case, our load is 360 pounds and it's resting at one end of the board. The board is 5 feet long. The fulcrum is 1 foot away from the load. Even though it doesn't state it in the problem, we should also diagram the distance from the fulcrum to our effort. In this case, it is 4 pounds. We should also include the equation, which is the mechanical advantage of the lever equals the length to the effort divided by the length to the load. We can substitute our known variables into this equation and solve for the mechanical advantage. In this case, the mechanical advantage of the lever is 4 feet, which is the distance from the fulcrum to the effort, divided by 1 foot, which is the distance from the fulcrum to the load. The feet cancel out, and we're left with a mechanical advantage of 4. We need to apply this to another equation, which helps us calculate the effort that we have to apply to the system. The equation for that is effort equals load divided by mechanical advantage. Again, we use our known variables to solve for our unknown variable. In this case, our load is 360 pounds, and our mechanical advantage is 4. We substitute those into the equation here, and we solve to understand that the effort for this system is 90 pounds. Now, what if we use a longer board? What if we change this to a board that is now 10 feet long? What does this do to the effort that we have to apply to the system? We still use the same equation, but we're going to be changing our variables. In this case, the distance from the load to the effort is 10 feet, but we don't use that in the equation, but we know that the board is that long. The distance from the load to the fulcrum is still 1 foot, but it's not included in the problem, but we should still include it in the drawing that the distance to our effort is now 9 feet. So let's plug that into our equation of mechanical advantage for the lever is equal to the length to effort divided by the length to the load. We use our known variables of the effort distance, which is 9 feet to the fulcrum, and our load distance, which is 1 foot to the fulcrum. Our feet cancel out, and we're left with a mechanical advantage of 9. We plug this known variable with our load into the effort equation. So we have 360 pounds divided by a mechanical advantage of 9, and this gives us an effort of only 40 pounds. By doubling the length of the board, we increase our mechanical advantage by more than twice as much in this particular equation. This is why a lever is so good at providing mechanical advantage.